Okay, so first of all, thanks to the organizers first for organizing this conference and also for giving me the opportunity to give a talk there. And thanks to all of you that are going to listen to my talk. And for those who don't know me, nice to meet you. Well, let's start, and we start with something more common, that is a matroid. A matroid is the datum of two things: a finite set E and a function that I define on the subset of E and takes natural number, positive integer numbers that satisfies three properties. In particular, let A and B be two subsets of E. I want this function that actually is the rank of my matroid to satisfy these three properties. The rank of a subset is between 0 and the size of this subset. If A is inside a subset of P, then the rank of A is smaller than or equal to the rank of P, and the rank of the union of A and B, two subsets of E, plus the rank of the intersection is smaller than or equal to the sum of the two ranks. Okay, this is kind of classical. It's the classical definition, but we will move to the q-analogue soon. If I have a matroid, I can represent it with the Boolean lattice. So I can take my finite set. For example, here I've done this for a very small one. And I can take my finite set and draw a diagram that represents my finite set and all the possible subsets with these lines that represent containment. And I can also keep track of this function, the rank, by using colorings. In particular, I use red color when the rank function goes up, and green when it stays the same. So I start with, well, yeah, I forgot something. Okay, here it is, the empty set, which has always rank 0. Well, the rank is between 0 and the size of the empty set is 0. Then I have these red lines that tell me that, for example, in my matroid, that actually is the uniform matroid U12, the sets with only one element have rank 1. So the red edge means +1 in the rank. And then I have these two green edges that say, okay, the total rank of my matroid, so the rank of the big set, is actually equal to 1. So I'm going up with the containment, but I'm not going up with the rank that stays the same. It is possible to prove that actually I have a matroid if and only if, when I make my Boolean lattice, I only have structures of this kind, so colorings done in this way. This thing is called a diamond, with this top and bottom and these two in the middle. And I can have a structure in which I have no increase in the rank, or I can have all red, so +1, +1, or I can have this structure here that is called mixed diamond, in which you see that there is a +1 here, +1 here, but here and here the rank stays the same. And then we have this thing that is called prime, in which the rank goes up by 1 here and here, but stays the same here. And it is exactly what happens in the example, in the small example that I have drawn for you before. Okay, so now we have a matroid. What I want to do is to work with the q-analogue of a matroid. What does it mean that I take the q-analogue of a combinatorial object? It means that I take finite sets and I substitute them with finite dimensional vector spaces. And so all the thing changes in the sense that an element in the, let's say, classical case, so in the case in which we are taking sets, becomes a one-dimensional space. This is the reason of my mistake in the lattice before. The empty set becomes the 0 vector space, and since I'm used to do this thing for subspaces, I usually draw a 0 in the bottom. The size becomes the dimension, and so on. Of course, the intersection remains the same. The union becomes the sum. The binomial becomes the Gaussian binomial. This Q here can be related either to the idea of working on finite dimensional vector spaces over a finite field FQ, that is what I actually do, or this Q may also stand for quantum, because there are also relations with this quantum. So I go to the definition of a q-matroid, that now is the datum of two things again, of a finite dimensional vector space over a finite field, for example, over a field, and a function on the subspaces that takes again values that are positive integers, satisfying the straightforward q-analog of the properties we saw before. So the rank of a subspace is between 0 and the dimension. Remember that size becomes dimension. If A is a subspace of P, rank of A is smaller than or equal than the rank of P. And then we have that the rank of the sum plus the rank of the intersection is smaller than or equal to the sum of the two ranks. So this is called the semi-modularity property. So it seems to be completely straightforward. I take my definition and I only substitute a finite set with finite dimensional vector spaces, sizes with dimensions, union with sums, and so on. Of course, I can do the same thing about lattices, also for q-matroids. In this case, I have the subspace lattice, so I might take my finite dimensional vector space, and I take the subspaces, and I use my lines for indicating containment, and again, I use red for +1 in the rank, and in green for rank remains the same, so there is no increase. I have made exactly the q-analog of the matroid that I sketched before for the classical case of sets. Okay, and also I have the same property as before, so I have a q-matroid if and only if I have only these kinds of diamonds in my lattice. So all 0, all 1, mixed again, and prime again. Okay, seems to be completely straightforward, and so it seems that I only have to change between sets and spaces, and nothing strange to do. But the thing is that I can define a matroid and also a q-matroid using different objects. So far, I only told you the definition that uses the rank function, so my space or set and my function R. But there are also other objects that can define a matroid, and the same goes for a q-matroid, and every kind of object has got its own axiom system. So for each object that I can use, I have the property that has to satisfy. Of course, you must end up with the same thing, so there are these so-called cryptomorphisms. That means we prove the equivalence of the definition that we give with the different objects. For example, some objects we can use are independent sets or spaces, depends on whether you're working with a matroid or a q-matroid, bases, circuits, spanning spaces, and there are several others. For now, I want to concentrate on the independent spaces, and just to tell you why things are not so easy. So here I have matroids and q-matroids. The definition made straightforward via independence. In the classical case of sets, I have my finite set. Of course, I know there are also infinite matroids, but it is definitely out of topic with respect to my talk, so I'm not thinking about the infinite case. And then I have my independent sets. So I have a family of subsets, and I have my axioms. I want it to be non-empty. I want that if I take two subsets and J is independent and I is a subset of J, then I is independent as well. And I want that if I take I and J, two independents, and I is smaller than J in size, then I can take something from J that is not already in I and make up a bigger independent set. Okay, let's try to make the straightforward q-analog. I take a finite dimensional vector space. I take a family of subsets, so I'm taking a part of this subspace lattice. I want it to be non-empty, no problem. I want again that if my J is independent and I is a subspace of J, then I have an independent as well. If I have I and J and I is smaller than J, in this case I'm talking about dimension, there should be a one-dimensional space in E such that it's contained in J, not already in I, and when I make the sum, I get an independent. Seems to be straightforward again, but this doesn't work. There is an example that I will explain very soon by Julius and Pelikan that tells you, well, if you take this kind of definition, so you take the straightforward q-analogue of the definition of a matroid, you end up with something that is not a q-matroid, in the sense that it's not equivalent with the definition with the rank. There is something wrong. So let's take E, that is my f2 to the power 4, and let's say my independent spaces are I and all the subspaces of I. So therefore, my axioms are easily satisfied in the sense that this is definitely a non-empty family. And of course, since I have defined it by taking a space and all these subspaces, also the second axiom that says that if something is a subspace or independent, it is independent, it's okay. And also the third axiom works because, well, everything is inside I, and so you can always take a generator and add it, and having something that still remains inside my I. So the three axioms are easily satisfied, but this is not a q-matroid. Let's consider A and B, two subspaces of E, and let's say that what is the rank starting from the independent? Well, it's the dimension of the maximal independent subspace. So therefore, let's see, okay, A, for example, contains 0, 1, 1, 0, but it doesn't contain the whole I, so it has rank 1. And the same goes for B. So rank of A and rank of B is 1. If I take their intersection, again, it contains 0, 1, 1, 0, but it doesn't contain the whole I, so A intersected with B as rank 1. But if I take A plus B, I get the whole space E, so it contains I. So therefore, I don't have anymore the semi-modularity property. R3 fails in the sense that I have 2 plus 1 that is not smaller than or equal than 2. So it means that taking the straightforward q-analogue of the definition of a matroid doesn't give me a q-matroid. The problem has been solved by Julius and Pelikan by adding a fourth axiom that has to be satisfied by by a q-matroid. And in particular, it says that if I take two subspaces and I take their maximal independent subspace inside, there should be a maximal independent subspace for the sum that is contained in the sum of the two maximal independent subspaces. In that example that I showed you, I4, this axiom was not satisfied because this was the maximal independent subspace of A and B, but the maximal independent subspace for the sum was not contained in it. And so, okay, problem solved. This is related to the fact that there are spaces that are called the loops, that are the one-dimensional spaces with rank 0 that come in subspace. So if I have two loops, their sum should have rank 0 as well, but in our example, it has rank 1. And it also related to the fact that we have sum instead of union. So there are new things arising when you make the sum instead of taking only the elements that were in your original sets. Let's go to some history of I4, in the sense that when I told you what was this axiom I4, I didn't tell you something important. That is, when I say maximal independent subspace, does it mean with respect to inclusion or dimension? When you also have the axiom I3, you can prove that the two things are equivalent. But if for some reason you still didn't prove I3, so you don't have I3, this makes the difference. So I was a little bit cheating when I was saying maximal independent subspace. What do I mean? Well, there are two notions of maximality that are actually with respect to inclusion and dimension. And from now on, when I'm talking about inclusion, I will use blue. When I'm talking about dimension, I will use red. It's only formality for saying maximality with respect to inclusion or dimension. There are many variations of this fourth axiom, and for example, I will show you 4 of them, and those that are in yellow here means that are the most practical improves. And as you can see, well, here we have dimension, here we have inclusion, and then I have again dimension and dimension. I mean, most of them use dimension. The idea is more or less the same, but here we are saying exactly the same thing with the maximality with respect to dimension, and here with respect to inclusion. So it's only if I take 2 subspaces and their maximal independent subspaces inside, I should have a maximal independent subspace for the sum that is contained in the sum of the 2 maximal independent subspaces, said with respect to dimension or inclusion. And then I have a couple of variations that are, for example, here I have 2 spaces. I is the maximal independent subspace of these, and there is a maximal independent subspace for the sum that is contained in I plus B. Or, of course, I can do something similar with the B equal to a one-dimensional space. What happens is that if I have a vector space and a collection of subspaces satisfying I1, I2, and I3, then these I4, I4 prime, I4 double prime are actually equivalent. And if I only have I1 and I2, it happens that I have equivalence between all the axioms that use maximality with respect to dimension, while the only one using inclusion is weaker. It needs the presence of the axiom I3. So the thing is that this axiom I3 is completely useless for defining a q-matroid if I use a version of I4 that doesn't use inclusion. So given I1 and I2, having I3 plus the version that uses inclusion or using one other version of I4 is actually the same. And so I can actually define a q-matroid with 3 axioms as soon as I do it in the right way. The same kind of thing holds for bases, in the sense that if I would make the straightforward q-analogue of the axioms for bases, I would stop here with B3, but again, I have the same kind of problem. And so a 4th axiom has been added. But the thing is that for these bases that are actually the maximal independent subspaces, you have the same kind of problem. So you have this family of subspaces, you want it to be non-empty, you want that if 2 bases are one in the other, they are the same, and then there are these axioms here. What happens is that, again, the axioms B1, B2, B4, so again with the maximal, in this case we have the maximal intersection between basis and your subspace, is enough in order to define a q-matroid. In this case, there is no problem between inclusion and maximality with respect to dimension, because it is not ambiguous, because I'm considering the maximal intersection of a space with some other subspace, so a basis. And finally, I have the same kind of thing with the spanning spaces, that are those spaces whose total rank equals the rank of E. So if I have a spanning space S, wait, let me write. If I have a spanning space S, it means that the rank of S is equal to the rank of E, so the total rank of my q-matroid. And again, I have my axiom system that is, until here, let's say, has inspired from the classical case, and then I have the 4th axiom that again makes the 3rd one redundant. So far we said, okay, we still can make the definition with 3 axioms instead of 4 if I use a good, in a good way, I mean my 4th axiom. But there is also the possibility to make alternative axioms, and to do that, I want to come back to an example that is similar to the one we showed, that is only a little bit smaller, to go inside to what happens with these axioms that work or not work in the q-analogue. So let's consider f2 to the power 2, and x, y, and z are the one-dimensional spaces. Suppose for a minute that I can have a situation like that, so in which I have x and 0 that are independent, but those two are dependent. The first three axioms are actually satisfied, but the fourth is not. Y and Z are not independent, so their maximal independent subspace is actually 0. But if I take their sum, I get E, whose maximal independent subspace is X. And so again, semi-modularity doesn't work. We can also see that by saying that loops come in subspaces. So since these two things are one-dimensional and they are dependent, so they are loops, the space they generate would be the loop space, so it would be completely dependent, but the space that they generate is E, so it should have been rank 0, and it doesn't happen. So things can be settled if I allow one other of this one-dimensional space to be independent. And in this way, so if I modify my B-coloring in this way, I get something that works. Indeed, what I was saying here is exactly, remember that loops come in subspace. If I have an independent one-dimensional space, all the one-dimensional space that are not in the loop space should be independent as well. And this is for one-dimensional spaces, but I can do that also for other dimensions by using an operation that is called the contraction. So I take, I start with my q-matroid, and I take E modulo x and the rank function that takes the difference between the rank of the subspace and the rank of x, the one you are constructing. So you can actually reduce to dimension 1. So my I3 said that if I have I and j that are independent, dimension of I is smaller than dimension of j, there should be x in j, but not in I of dimension 1, such that I plus x is in I. I can take modulo I, I can take the contraction. I have here a one-dimensional independent space, and so all the things that are outside the loop space of this should be independent. And since we have something that is not a loop, the codimension of L should be bigger than or equal than 1. And so, well, all subspaces of this form are such that they should be such that I plus X is independent. And this lead us to an axiom, a new axiom that says, let's take again I and j, I is smaller than j in dimension. But now, instead of saying only that I have to pick something here and adding it to I in order to have a bigger independent space, I say, let's take a codimension 1 space that contains I but doesn't contain the whole j. And then for all the x's that are not in my codimension 1 space, I plus these x's is independent. It is clear that new I3, this new axiom I3 implies the old one, in the sense that j was not completely contained in x, so there is also something in x that added to I makes independent my things. But there is something more, I'm adding more things. And actually this axiom is again equivalent to the independence axiom. So it's another way to define a q-matrix with 3 axioms. I can do the analogous things also for bases and for spanning spaces using more or less the same principle. And one thing that one can prove is in order to use these axiom systems modified, without I3, is that another kind of object, the minimal dependent spaces, actually, the circuits can be proven to be equivalent to the independent spaces in a direct way by using this axiom system. Okay, I have, let's say, finished my exposition. I thank you for your attention, and also thank you again also for organizing this conference, and thanks for all the people who listened to my talk.
Great, thank you very much, Michela.
Thank you. Now I don't know whether there is anything in the
chat. I haven't seen anything yet. Yeah, but
let's see, because I don't see anything.
Does anybody have any questions for Michaela?
Sure, I had a question.
Okay.
So one of the reasons that matroids are so useful, ordinary matroids are so useful, is because there are all sorts of examples, such as graphs and vector spaces and so forth, so that you can prove one fact about matroids in general, such that, say, for example, that all bases have the same number of elements, and it automatically gives you various theorems in these other areas in a uniform way. Are there naturally occurring families of subspaces that you can have the same sort of effect with these q-matroids?
Okay, what we can do with q-matrices is connecting with code in theory, actually. So what we can do is relating, for example, representable q-matrices are rank metric codes. So we have connection with that. There is still no connection with the q-analogue of a graph, but I hope that in the end, I mean, I'm trying with Relinde also that, but for now there is no q-analogue of a graph, and it would be great doing so. But for now, yes, there is the thing that, vector rank metric codes are q-matroids. And rank metric codes in general are q-polymatroids. So this is what we can do.
Gotcha. Okay, thanks.
Great, excellent question, Bruce. There's now a question from Yuan in the chat.
Yes, there is a new notion of dual q-matroid, of course. So I can point you to the paper with the first definition of duality, even though we also use that, because I think it is in, yes, it's definitely in the Julius Pelikan paper. If you want some bibliography on that or something like that, just write me an email. I hope that in the website there are emails. If not, I can share the screen or write it in the chat. So if you want to contact me for more on that, but in any case, yes, there is the duality. Maybe when I finish the talk, I will write my email address in the chat, so that if someone wants to read something on that, I can send links or so.
Sounds great.
Thanks.
Yeah. Any other questions for Michaela?
Is there a q-analogue to oriented matroids at all?
Okay, as far as I know, there is still no q-analogue of an oriented matroid. Well, consider that it's only a few years that we are working on, that people are working on that kind of q-analog. So we are developing the basis of the theory. I mean, also in the papers I cooperated in, we were working on cryptomorphisms, for example. So, I mean, we are establishing, I'm one of the people who is trying to work on the foundation of that. So there is still a lot of things to do on the q-analogue of matroid.